To stick around.
My name is Andrew Kille. I'm excited to start off the Quantum Mini Symposium, hopefully on a high note. Today I'm going to talk about QuantumSymbolics, which is a Julia package meant to compute symbolic expressions of quantum states and quantum operations, and then enable the user to efficiently convert them to different numerical backends. I'm probably going to talk pretty generally about these different backend representations. That'd be a bit pedagogical, but I think like my main motivation with this talk is to kind of generate some discourse about like integrating different Julia quantum packages together. I'm sure that's happened in the past at different JuliaCons, but I hope with this new embryonic package we can generate new discussions. I guess a few notes about the history of this package. So it started out as sort of a nice like under the hood tool for the NSF's Center for Quantum Networks. They have sort of like a full stack quantum networking simulator where they want to simulate not just like analog quantum dynamics in like your quantum hardware, and maybe you want to compute some material properties, but they also want networking scientists to be able to run discrete event scheduling on their quantum network, or do some sort of like entanglement swapping, or like some their favorite quantum networking protocol. So the idea is that QuantumSymbolics can kind of make this easy so that networking scientists don't really have to worry about any of these like classical algorithms or backend details in different Julia libraries. So I basically do some contracting work to help contribute to that. I just started as a PhD student at NYU, and now I'm at the Flatiron Institute in their Center for Computational Quantum Physics. So right now I'm interested in tensor network representations of continuous variable quantum systems. So I'm not going to talk about that in either of the talks today, but I'm happy to talk about that during the sessions and such. Okay. One other shameless plug. So Stefan, who kind of runs the full stack networking simulator with the NSF, he also has sort of this mini grants and bug bounty program where it's kind of meant to get junior developers involved in contributing to his software. And they can do like Google Summer of Code style projects, or if they don't really know how to contribute to open source, they can do like small pull requests and fix bugs and stuff like that. So I guess anyone watching who's a junior developer who wants to get their foot in the door, this is a good way of doing that. It's a fantastic way. So you can find information about that on the Quantum Savory GitHub repository. Okay, now with that, so oftentimes as quantum physicists, when we're trying to model quantum hardware, some quantum dynamics, we want to do a few different somewhat simple tasks. So maybe we want to take a quantum state and represent it in some numerical form, and then compute the Schrodinger evolution of that quantum state. Or maybe we don't really care about the underlying quantum dynamics and we want to model some sort of noisy channel. It could be very arbitrary, and then implement some sort of error correction scheme on that physical channel. Or, if you're interested in dynamics or in like a chemistry application, you can, compute the average energy of a Hamiltonian of a quantum system. But I think if you want to do all of these things, like a lot of people want to do like within the NSF and designing quantum networks, it's rather difficult because you have to worry about different backend representations and deal with different Julia quantum libraries like Quantum Optics, Quantum Toolbox, among others. So you kind of deal with two different problems. One is like, okay, what's the actual like classical algorithm that you're going to use to do some sort of quantum dynamics or error correction protocol? There's a few. I'm just going to list them. I'm sure most of you are familiar with them. So the first one's a state vector simulation, right? Where that's kind of the naive way of doing things, where you take a quantum state and then you encode its amplitudes into this large matrix that scales exponentially, really, really fast. And that's good for like very small systems when you scale it to the many body, but it's pretty poor because your matrices are so large. You also have a stabilizer tableau, which you can use for quantum error correction protocols, where you can use a lot of symmetries and simulate like a relatively large class of quantum circuits with this algorithm. Or you have tensor networks, which is what I'm currently interested in, where you work in the many-body case and you basically take a tensor product structure of your quantum system and then compress it down with some sort of linear algebra decomposition scheme. And then it's up to like, okay, what kind of solvers do you use, like DMRG or Belief propagation, that sort of thing. And then there's others where you can kind of work on different classes of quantum states, like phase space representations, which just to advertise, I'm going to talk about that later today. There's polystrings and neural network quantum states and so on and so forth. But really, like, none of these classical algorithms, of course, like, enable you to simulate like an arbitrary quantum system, right? Like, so tensor networks are really bad at simulating like high entanglement quantum systems that have a lot of connectivity. State vectors, you can't go past tens of qubits. Stabilizer tableau, it only simulates like a small class or medium-sized class of quantum states. And then on top of that, like, if you want to choose a specific quantum state representation, you have to choose a library. So if you're interested in Julia, like for state vectors, there's quantum optics and quantum toolbox. Stabilizer tableau, there's quantum Clifford. Tensor networks, there's iTensors and TensorKit. And really, like, if you're trying to move back and forth between these different representations, it's like really challenging to do, right? Like, there's really no, like, at the moment, in my opinion, like a practical workflow to go across these different packages. So it's really a question of like, how much time do you actually have to learn to like understand the syntactic sugar that some of the package maintainers like developed for their own specific package, and then maybe they have really bad documentation, so that you have to deal with that as well and look into their source code. So our attempt of dealing with that, it might not be the best attempt, but we sort of have a prototype for dealing with this, which is that we have the user input some sort of symbolic quantum expression that they want to express within QuantumSymbolics, and then they throw it into a numerical backend, and they don't really worry about any of the implementation details. All they really care about is like the end result. So maybe they care about the state vector representation after the end of the unitary evolution, or they want the stabilizer tableau, but they don't want to go through all the details of like understanding the string macros in quantum Clifford, or you want to compute some sort of ground state energy. And the way that you sort of do this as a user with QuantumSymbolics is the following. So I'm just going to make up a package that I call my backend, and I'm going to define this symbolic expression. So it's just a simple expression. You have the application of a C0 gate on like a tensor product of Pauli Z eigenstates. That's just your 0 and 1 operators. And you create the symbolic expression, and I'm going to get into the details of how the internals work later. But you basically use this express functionality in QuantumSymbolics, where you take the symbolic expression and then you convert it to your backend. So maybe you have to define some configurations that are special to that backend, but in this case, you get a state vector representation of the applied C0 gate on this quantum state. And really, why this is, I think, powerful is that you can switch between numerical backends like really, really easily. Like maybe one backend is really, really slow for this quantum operation, and another backend is really fast. So just to give an example, if you use GABS, which is supported in QuantumSymbolics, it's kind of a phase space Gaussian quantum information package. You can define a single mode vacuum state and then apply a squeezing operator on that vacuum state, and then you get out a Gaussian state. And this Gaussian state scales like n squared, so you can use it for really efficient simulations of Gaussian quantum information. But then if you also want to like compute more sophisticated like non-Gaussian dynamics, you can just express that state in quantum optics and then evolve it using their time evolution solver. So there's kind of different ways of expressing the same symbolic quantum object with these different packages. So at the moment, we have a few different packages supported. We'd like to have more, and I'd love to talk to anyone who's interested in like implementing their own numerical packages with quantum symbolics, but so far we have quantum optics, and then we're really close to getting quantum toolbox integrated within quantum symbolics, and then we also have like a backend for just converting state vectors to pure Julia arrays, and then you can maybe use like more directly SciMLs, like differential equation solvers, and just plugging in those state vectors into there. And then we also have a stabilizer formalism with Stefan's quantum Clifford package, which performs like very heavily optimized stabilizer calculations. And they're also working on sort of a graph state simulator as well, which I'm really excited in having support for in the future. And then right now we're working on integrating quantum symbolics with I-tensors, although that takes a lot of work because, you know, you could have like a matrix product state backend, but you could also have like very arbitrary tensor network geometries. And it's a bit complicated. And also I-tensors is developing a lot as we speak, probably. And then there's also GABS, which is what I'm going to talk about later with the phase space representation of quantum dynamics. So just some internal details. The way we kind of make this possible, I don't know if it's necessarily something to brag about per se, but we have this package that kind of establishes like a common namespace, like interface conventions for these different packages. So like, and it's called quantum interface. And it basically defines abstract types like abstract operator, abstract state or state vector or something like that. And then all of our packages basically subtype these types are in quantum interface, and it makes the operations within quantum symbolics like much easier. And then we also define methods that we hope everyone will use within that ecosystem, like taking the partial trace of a quantum state that'll just be ptrace or something like that. So as you might notice with this kind of Wiggly diagram, there's like not all the packages supported in quantum symbolics are like underneath this quantum interface. Like I-tensors isn't in here, quantum toolbox isn't in here, but it makes things much easier on our end, like on the developer side of things, like just sticking to this sort of interface. Okay, so how do we understand the quantum symbolic expressions implemented in quantum symbolics? So we take these abstract types from quantum interface, and then built within quantum symbolics is the Symbolics.jl like computer algebra system, which is created by SciML. It's pretty good, and it's very well maintained. And they basically have this symbolic type. It's called Symbolic, and it wraps around like another type, and that basically defines it as a symbolic representation of that type. So for example, we have this definition of a symbolic Fock state, and really we only want to attach like as much information as like as minimal amount of information as we can. So we just attach like the number of particle excitations in that Fock state. So like could be a single mode vacuum state or like a one photon state. And that's basically how it works. And by subtyping it with symbolic, we can do things like symbolic simplification rules and expansion rules like you kind of see in Mathematica. Although we're kind of still working on that a bit. Yeah, and this metadata macro I'm going to talk about a bit later coming up. So then when you create some sort of symbolic expression, what you do is you have these symbolic types like in the bottom right corner, Y gate and X gate. And then if you want to take a tensor product, you create, you use this tensor symbol O times, and you create a symbolic tensor operator. And then if you want to keep building it up, you just create more types that support like scaling and addition and so on and so forth. And this is kind of how like we have an abstract syntax tree, right? Like we just do simplifications when we can, although we're still kind of working on that. And we'd be open if there's any like really involved symbolics people in the audience that want to talk about like how we can do symbolic simplification for like really high volume quantum systems. I'd be interested in talking about that. Okay, so about the metadata, this is something that we use for our quantum networking simulator, where oftentimes these numerical conversions can be a bit computationally expensive. And we don't want to do like a bunch of tensor products, say, of like a state vector over and over again. So what we do is we cache a numerical result after we do this express conversion. So here I have that single mode vacuum state, and I express it over to the GABS representation and defining some sort of symplectic basis, which I'll talk about in the GABS talk. And then there's metadata attached to that symbolic expression that now basically caches that resulting Gaussian state in the GABS formalism. And then if you, again, convert it to the quantum optics representation, and here I'm defining some numerical cutoff that, a Fock state's in an infinite dimensional Hilbert space. So if you actually want to simulate it on a computer, you have to truncate it at some number. So I'm defining that. And then when I convert it to quantum optics, I also have this cached quantum optics representation attached to my symbolic state. And again, this is really good for I have this quantum object sitting at this register, and I don't want to keep converting these symbolic expressions back and forth to these different backends. So caching it is like a really nice way of kind of avoiding those computationally expensive operations. And this is just an example. I'm not going to get too much into the details of this because I know there's one, maybe two people giving a talk on this later in terms of creating these large-scale networking simulations. But this is just kind of how like a front-end networking scientist would sort of see this, where they only really care about these different entanglement generations going on between different quantum registers. And they really don't have to worry about the quantum optics details, like the implementation details, like their Schrodinger solver or, generating certain states. All they really want to do is simulate these different networking protocols. So I guess future directions. So in the future, we'd like to add some more sophisticated backends. So I'm sure many of you are going to talk during this mini symposium about numerical backends. We'd love to have them integrated if we don't already. We'd like more apparent use and more direct use of the different solvers within this different backends. So like, for instance, in quantum optics, they have, obviously a Schrodinger equation and a master equation solver, but they also have like Monte Carlo and stochastic solvers as well. So I think like enabling the user to like directly define that if they want to, I think would be a good tool to have. And as I talked about earlier, we can maybe do some more worrying about performance in terms of symbolic operations and stuff like that. And then adding more configurations, letting the user have a bit more freedom in doing that. So with quantum optics, they have like these lazy operators where you don't want to directly compute a tensor product between large quantum states. So maybe letting the user be able to compute that would be quite useful. So that's all I have. Thank you very much for your attention. I'm happy to answer questions.
Thank you. This was great. And we already have our first question.
You've got this system that can use the different backends. Does the user say which backend to use, or are you automatically choosing that somehow?
They get to specify which backend to use. So you can see here, they're expressing this single mode vacuum state with quantum optics. So that like sort of representation type just sort of specifies convert this symbolic expression to the quantum optics backend, and then we have a numerical result. Yep. So they definitely do have freedom there.
This is really great. Thank you for the awesome talk. I was wondering, do you guys have any integration with the ZX calculus package? Is that something that you're considering doing?
I haven't put a lot of serious thought to it. Yeah, I think it'd be cool though. Yeah. I don't have any well-developed thoughts about that, but I think I'd be very interested. Yeah.
PR's welcome, perhaps?
Always. Other questions?
So this is fantastic, and we definitely will have to talk because we have a lot of state representations. We do a lot of control work, and one thing that we kind of bump into a lot is not just representing states, but like kind of the operators also, and like time evolving a unitary or a channel or things like this. Is that something that's also kind of like in the mix as a thought here? I mean, you can imagine like you can always get the identity by just picking a basis of states, but like that's something that it would cover kind of half of the things that we normally care about, and then we'd still have kind of half of what we interact with hanging around.
Yeah, that's a good question. So I think what a lot of this software currently does is like we have some sort of predefined state symbolically, and then we convert it to whatever, and then the user at this moment in time has to then express that converted state and then put it into like some sort of solver or something like that. But I think it would be really cool to then like have some sort of integration with all of the solvers and then do stuff like that, like time evolving unitaries and all that. So we don't currently have a lot of support for that, but we'd like to.
Okay,
Yeah.
cool. All right, yeah, definitely, yeah, strong endorse. That would be great. Yeah.
Okay, sorry, I came up with another question. So also I'm interested to learn, how does this integrate with iTensor's auto MPO system? Like, is the idea is it's basically a drop-in replacement for that, or?
We are still working on that, and we're definitely workshop because it's tricky. Yeah, but I would actually love to talk about that with you because I think you. Yeah.
I guess a question on my end. Trees, abstract syntax trees are not type stable, and Julia hates that. So, any thoughts on how to make that efficient?
I don't think Symbolics is probably the way of making that more efficient. I know that Roger, with QEra, I think is trying to work with that. Like he has Moshi and then Expronicon, which are kind of these nice symbolic abstract syntax tree packages. But I don't know the full details of that. So I don't know if I have a way of working around that. Symbolics is a nice, well-maintained package for Julia computer algebra system, so I'm just kind of sticking with it.
Sounds good. More questions.
So I don't know, I might have missed this, but like presumably like you're having symbolic representations for non-commutative operators. And I'm wondering if this kind of would play with the symbolics package where you could differentiate with like, say you have a scalar parameter times a non-commutative operator and some sort of product something. Can you differentiate through these kinds of things and do kind of symbolic calculations like that?
We have not tried any sort of auto differentiation of.
Okay.
I want to say there's a quantum cumulance does something along those lines.
Yeah, I remember playing around with it. I couldn't get it to do what I wanted it to do.
Yeah,
So
it's fair enough.
yeah.
Yeah.
That would be useful though.
Mm-hmm.
So not only PRs welcomed, feature requests welcomed, posted on GitHub. Other questions? If not, let's adjourn here, and I believe we have a lunch break, and then we're back here. So let's thank the speaker again.
Also, just a quick note for anybody who was at the workshops yesterday. Today lunch is 90 minutes long, so we'll be back at 1:30. And then we have another break mid-afternoon for the keynote. So the schedule's a little funny today, but 90 minutes from now, you should return if you want more quantum content, which you should.